Okay, I think maybe we can go ahead and start now. So, hi everyone, welcome to the optimal pitch, overcoming shading challenges in the Nordics and beyond, with the next slide introducing myself and my colleague Julian. So I'm the Senior Account Executive for the Nordics market at RatedPower, working in the business team. I'm accompanied today with my colleague Julian, who's our technical advisor from the customer success team, and who is responsible for the Nordics market as well. On today's context, we'll be discussing with you the optimal overcoming shading challenges in the Nordics and beyond. We will be showcasing pvDesign and giving you the solutions that we have came up with for this specific issue about the pitch. And then finally, we'll leave about 20 minutes for the Q&A session. So feel free to drop all of your questions in the questions box, and we'll get to them in the Q&A session. So just to give you a small overview of pvDesign, for those who do not know it, pvDesign is a cloud-based software that you can easily access through your Google Chrome or Firefox. What pvDesign does is that it optimizes design engineering of utility-scale photovoltaic plants. You have no limitations in terms of designs per project. You can create as many designs as you want to make sure that you have the right design for your project in terms of the requirements that you're looking for. And in addition of that, you can easily compare them to make sure that you have the comparison analysis done based on the requirements that you require for your project. And the final cherry on top is basically the technical documentations that you generate after finishing your design. So these technical documentations will follow the reports, the spreadsheets, and the set of drawings. And the best part of this is that all of the technical documentations that are generated after you're done with the design they come in editable format, so you can easily edit them and make them more to your own specific needs and requirements. So with no further ado, my colleague Julian will go ahead and explain to you how to overcome the shading challenges in the Nordics. So just as a reminder, feel free to drop any of your questions in the questions box. Thank you.
Thank you so much, Ghada. Yeah, no, that's great. Great introduction. So yeah, welcome from my side. I will jump right into it. So first slide here, I want to talk a little bit about the context. So we are in the Nordics. I show a map of Europe here, and PVGIS, they had that map to showcase what kind of irradiation we can expect, what kind of global irradiation, and in high latitudes, we can go for like 800 to 1,100 kilowatt hours per square meter. What does that mean for our plant? That's the specific production, and in this case, PVGIS estimated 600 to 800 kilowatt hours per kilowatt peak installed for a plant at a performance ratio of 0.75, so around 75%. And that's, of course, much different than if you would go to the south of Europe. There's much higher values for irradiation there. What's the reason for that? Of course, and that's the next point, the sun elevation in the higher latitudes, especially of course in the winters, but generally the sun doesn't reach as high. We have some far shading casted by the horizon values, like the landscape, which our PV plant is kind of located in. And all of that together will result in shading issues, in losses due to shading. And we try to kind of figure out today what kind of parameters we can change in our design for a PV plant and how we can find that optimal pitch we want to achieve. So next slide here, we want to show a little bit about our software, what kind of parameters really affect that shading losses. And of course, first of all, it's the pitch distance. Just to be clear on the same page here, we define it from one border of a structure to the exact same border of the next structure in the next row. So it's the clearance distance, the gap between the structures, plus the width of that structure. So of course, if we change the pitch, we will have more or less shading losses. Next up, the tilt angle, of course, if we adapt that, if we change that, that will affect the shadow casted to the next row of our modules, so that can affect that as well. And then lastly, I wanted to show that, or just showcase a little bit, the string arrangement. So of course, if we select our strings to be aligned in an axial direction, which is highlighted here on the top, for example, if there is a shadow coming from below, only the yellow string in this case would be affected. It would not create as much power as we would expect. So, but at the same time, the dark blue string can operate on full power. So this is usually the preferred arrangement, whilst the pitch grouping, which is called that in our software, is when you arrange each string more into like a group. But imagining there's a shadow coming from below, then all these 3 strings will be affected, and they would all have a shading loss and a mismatch caused by that shading. So these 3 parameters are kind of influencing that. Diving more into a more like calculation background and combining these parameters, I wanted to show you that slide, and I will start with that image first. So what we can see here is we can see the sun, and we can see a tilt angle, we can see the sun elevation angle, and we can also see our module and our rows of modules here. And basically, starting first, what you can do is you can take that tilt angle, and based on the tilt angle and the module width, we can calculate a height difference. And knowing that height difference will help us a lot to then go further and calculate what pitch or what row spacing is needed to ensure no shading at that given sun elevation angle. So next, we would take that elevation angle at a specific point in time. So maybe at solar noon in the summer, it can be solar noon in the winter, depending on what we want to analyze. And then we can then use that to calculate our module row spacing by just taking that height difference we calculated before, dividing it by the tangents of the sun elevation angle, and we would get the module row spacing. What does that module row spacing mean? So basically it means that at that sun elevation angle, we don't have any shadow casted on our next module. And as I mentioned before, our pitch is not defined by the module row spacing only. So we would have to add the cosinus of the tilt angle times the module width, which is essentially the projected module width on the ground, to add that all up to the pitch distance overall. And with that background, we can know, okay, there can be some factors who affect or have an effect on our pitch distance. And based on that knowledge, we can then use that in pvDesign later on to optimize our pitch. But what kind of goals do we want to achieve? I mean, the optimal pitch can be seen from many different perspectives. So I just wanted to highlight here, let's say the common ones, and then the specific case scenarios, which can be a lot, of course. First of all, the maximum energy yield. Of course, if you want to achieve the maximum energy yield on your area, that usually means a quite low pitch distance. That will increase the shading losses. It will also increase the total costs, because you would squeeze more modules, more structures on that area. But if that's your goal, if you want to achieve maximum energy yield, this is the goal to go. We can also optimize our pitch towards the minimum LCOE, for example. We can think about achieving the highest specific production, so the highest energy yield from our peak power installed. And that usually would mean we would have to go for a larger pitch distance, of course, because if we have less shading losses, our modules can produce more energy over the year. That will mean an overall larger pitch distance in this case. And then, of course, the specific case scenarios, which are in the middle in between, it's either to reach maybe a specific LCOE. So in case you have a goal to achieve, this is the target. Or maybe third parties, they set some limitations. So imagine you're not allowed to go under a certain pitch. You have to at least have 4, 5, 6 meters of pitch to ensure that vehicles pass through. Or maybe the requirement is that only 60% of your area can be covered by modules due to environmental restrictions. So all of that can be specific case scenarios, which would kind of steer that target towards the optimal pitch. And then lastly, what I showed here on that slide is reaching a certain performance ratio. And this is what we try to aim for today in the showcase in pvDesign, because in the first slide, we saw that PVGIS had some numbers on specific productions for a performance ratio of 75%. So we will try to achieve that today with an example design. So with no further waiting, I will go and jump into our software, pvDesign. I will quickly open that, drag it here, and now you should be able to see the interface of pvDesign. For the participants who haven't used the software yet, it's a cloud-based software, as Ghada mentioned already, and you can see your design here. And what I can do now, I can clone that design and jump into the design process. So when I do that, you can see all the parameters you can change. Here on the top, we have different options to select the parameters and to change your design. But as we are today interested in the pitch, we will go for that. What we see here is basically we see two areas. We see some restricted areas. You can see our module rows already, and I imagine that it's clear that this is far away from an optimal pitch. It's a very big one. We can double check in the layout tab. If I click on distances, we can see we have 40 meters of pitch, so quite a large one. So we will today try to aim and to get that optimal one to reach a performance ratio of 75%. What kind of equipment did I use? I have a bifacial module in this design. I chose a string inverter of 185 kVA. And for the structure, you can also already see it a little bit. It's a fixed structure facing south, and it's a 2V configuration. And with a tilt angle, if I scroll down a little bit more, here on the tilt angle, you can see I chose 30 degrees. And we are generally located in southern Sweden as a background. Okay, perfect. So how do we get that optimal pitch now? So what we can do in pvDesign, we can use that multiple design option here. We call it batch design. I can click on it, and then I have different options, but I will of course use that pitch distance option here. And now I can say, where do I want to start? Do I want to start at maybe the minimum pitch? And the software already indicates what is the minimum pitch I can put. And this is due to the width of our modules. So we cannot go below that because our module width is, and the structure width in total is 3.95 meters. So I will go ahead and just start from the minimum one, because we want to see, okay, we start from the minimum, which we would expect will give us the highest energy yield, but we can see that later. And then I would first go in quite a large step value. I would just go 1 meter steps. And then if I update, I will end up after 10 designs at a pitch of 12.95 meters. I can refresh the table. Here, I have to set this to 100 because we don't have more than 100% GCR. And with one click now, and I will go ahead and do that, with that one click, I will generate 10 designs and they will run on our servers. It doesn't require any high performance computer, and it will simulate the 10 different pitches for me right now. While this is happening, I will dive into the existing design I showed you earlier with a very inoptimal pitch and just show you how can we find out about the shading losses, what does the software give us. And in this case, it gives us up here specific production quite high. As I mentioned before, we would expect in southern Sweden, let's say 600 to 800 kilowatt hours per kilowatt peak, according to pvGIS. We have a quite high performance ratio, of course. There's not much shading going on, and we can double check. If we click on energy, we can see that basically the software gives us energy injected to the grid. We can already see the sun elevation angles. So basically here you can see what path does the sun take over the year, what kind of far shading do we have. So there is a hill on the right of our, or to the east of our plant right now. And in more detail, we can check here on the right the losses which the software calculated. And if I scroll down a little bit, I can see the area shading. And this is the shadow or the shading losses we can expect from this design. And as we chose a very large pitch in the beginning, it was 40 meters, this is 0%, almost 0%. So we are very good here in terms of shading losses. But if I look at the energy, which is the energy yield per year, 5 gigawatt hours for that size and for that, that PV plant is fairly low. So we're far from optimal, and this is the goal today. So let's see, okay, we can see that the 10 designs are created already. I can mark them all. I will deselect our starting design. So now they're all marked. And what I can do now in pvDesign, I can compare that. I can click on compare. And what happens? I see all these designs in a row. I have a great overview to see what results changed, what is my optimal pitch. And I will first order my designs by specific production. So I will start with the lowest. We can double check here. The lowest specific production is of course the lowest pitch because we have the most shading losses here. But we can see, as expected, we get the highest energy yield here. So if that would be our goal, we are done already. This is fine. We know this is our favorite design if we in terms of energy yield. But if I move a little bit to the right, to the other end, I see the other extreme, and the other extreme was the highest pitch. So in this case, it was 12.95 meters, and we can see, first of all, the performance ratio is really high. We can see that our specific production is also the highest, and the LCOE is quite low. So it's the cheapest energy produced actually. But, and that's very important here, that energy yield overall, 15,000 gigawatt hours, that's not very high compared to what we had before. We could reach up to 29,000 gigawatt hours. Pardon, sorry, it was not 29,000, it's 29 gigawatt hours, of course, 0.641. So yeah, we want to find the optimal one somewhere in between, because on the left, this is too much shadow maybe, and on the right, we have not enough energy produced. So as I mentioned, we try to achieve, and we can follow up here on the performance ratio. We can see that we want to achieve something here in between. 76, okay, maybe a little bit more to the right. Yep, 70 here. So we want to end up somewhere here to achieve that 75% performance ratio. And how can we do that? Of course, same process now. I will go out. I will start with that design 148. This is the one with our smallest pitch. I will again clone it. So we do the same process all over again, just a bit more refined. And this is the great feature and the performance of pvDesign here. We can just generate multiple designs in a few minutes. So I will click again on generate multiple designs. So now what we do, we know that 3.95 meters was too small. We will start at, let's say, 5.95. In this time, we don't do 1 meter steps. We go with 25 centimeter steps in this case. And that would mean in the end, we will reach 8 meters. So somewhere in between there, we will find our optimal solution. Maybe I thought I would put here this, sorry. I think now we're ready to go. Exactly. So somewhere in between there, we hope to find our performance ratio of 75%. I hit the same button again, generate design, and the same process happens all over again. What I will do now is, just for a better overview, I will click those designs which I know I want to discard because they were not the ones I was desiring. So I can mark them here just for a better overview. Can do that here quite quickly, delete them, done. What I didn't show you yet was I just imagined that the shading losses are higher for the design with the lowest pitch, 148. And we can just double check. I will click on it again. I will be guided to our final design. From the first 2-day layout, this will be loaded in a second. We can see already, okay, the pitch is much lower. We can see more modules on our area, so it looks much better. But if I go into more depth and I will open the energy tab here, we can scroll down directly to our array shading. Okay, in this case, I can see that it's 11%. So it went up from 0% to 11%, which is quite large. If we're okay with that, that's fine. But I assume that this is that we can reach something better in the middle. And this is the goal for today. So I went out. The design's already done. I will do the same process again. I will mark all of them. That's done. I will deselect the ones we already know, and these are these 3 designs. So I have my 9 designs ready. I will click on compare again. Now in a more refined resolution. So I will do the same order from lowest to highest specific production. We started with 5.95 meters, and I will just go straight to the result. I will just scroll to the right, and I will see, okay, here, this design I would assume is closest to my 75.2% of performance ratio. So in this case, we have a pitch of 6.7 meters. We reach 892 kilowatt hours per kilowatt peak. It's even higher still than what pvGIS expected from that image in the beginning. we reach an overall energy yield of 25 gigawatt hours, or 25.8. So in our specific case scenario now, when we wanted to achieve 75% performance ratio, it's done. We know it's 161, that specific design. We can even mark it as our favorite if we want, and then delete all the rest. And basically, this is how we improved and how we find the optimal pitch for our specific goal. I will take a chance and go back to our slides. In the slides, we can have a better overview of the results. So just to kind of sum up, what did we get? And I listed first on the left our specific case scenario. So it was in southern Sweden. We had a global horizontal irradiation of 973 kilowatt hours per square meters, and this was comparative. Like we could compare it to the image of pvGIS. What structure did we choose? A 2V configuration, a tilt angle at 30 degrees, bifacial module, and a string inverter. And our goal was to achieve that performance ratio of 75%. And then here on the right, I marked our 3 designs, starting with the left one, which was the smallest pitch. We just wanted to see what can that, like how is the performance of our design with the smallest pitch. We achieved a fairly low specific production here. We have an energy yield, which is the highest, of course, but we weren't satisfied with that. So we went to the other extreme, and that's on the far right, the largest tested pitch of ours. It's 12.95 meters, and this gave us the best specific production, the highest performance. However, the energy yield, and this is seen here in the below our specific production, this is fairly low. So in the middle, we went for the 75%. We achieved it more or less, like almost 75% straight. And this is how we kind of use pvDesign to find that optimal pitch for our case scenario. I know this process was quite quick now, but if you have any questions now, we would dive right into the Q&A. Any questions on the software, any question on the process, on the optimal pitch, you're more than welcome to ask them now. And you can just type them into the GoToWebinar chat box, and I'll be happy to answer them for you.
Thank you, Julian. It was a great presentation, very insightful.
Thanks.
Thank you. I actually have a couple of questions, so I might as well just read them for you. Okay, so you can show us your screen. So the first one is asking at which time of day we should calculate solar angle for shadow calculations.
Yeah, that's a very good question. I will go back to the slide here. Well, it's a question of how you want to optimize your design. We have different approaches here. I heard many feedback that they usually take the solar noon, so when the sun is the highest. But then, of course, there's the question, what day do you take? And for example, in the Nordic countries, the winter month can be sometimes users or the talks we have, they say that in the winter month are ignored entirely. So they take, let's say, the spring or the autumn month. So you would take maybe at the 21st of March or 21st of September, the sun elevation at solar noon. And this could be a first indication on a good pitch distance, I would say. Of course, you can also do a range. So another approach would be you start not at solar noon, but maybe 2 hours before that and 2 hours afterwards. And during that kind of window, you want to ensure no shading on your array, on your modules. And then you would do the first calculation with 2 hours before solar noon. You would do the same calculation with 2 hours after solar noon, so with 2 different solar elevation angles. And then you would know, okay, in between there, we would have to ensure that no shadow is casted on our modules, and that pitch we will take. So there's no clear answer, unfortunately. It's depending on how you assume your energy yield calculations the best.
Perfect. Thank you, Julian. That was thorough. Also, other question: would a performance ratio of above 75% be optimal for single-axis tracking?
That's a good point. And that's it's very interesting for trackers, for single-axis trackers especially. I mean, I can go just back here, and just as an example, we can just choose an example design. I will just go for the ones with the largest pitch as an example. I will clone it, and I will just do that. I will just choose a tracker, and that can be done in pvDesign by choosing the equipment, changing the structure to a single axis tracker here. In this case, it's a 1V configuration. We don't really bother about optimizing the area here. I mean, I can adjust it a little bit with one click here, optimizing it a little bit, but from my personal experience, I would assume that 75% for single axis trackers is not enough. You can achieve much more because the shadowing, the shading losses are much less, of course. So I just check that, and we can double check what pitch distance we choose. I think I chose the one with 12.95 meters, so already quite high. And once this is simulated, we can check how the performance ratio occurred. But while this is happening, actually, I will do another design because I just realized it would be perfect to compare if we choose a tracker and just keep the same distance we just achieved, and that was 6.7 meters, if I was correct. I think that was, yeah, that makes more sense. So 6.7 meters here. I have to, in this case, select the same tracker again. And once this is done, we can then better compare our performance ratio. So let me regenerate this. Perfect. Okay, the other one is already done. We can double check if I click here. So this was the tracker we just selected. We have a high performance ratio of 85.8%. I can double check which pitch did I use. And it was, actually it was 5.7 meters. Okay, so this was even a quite low pitch. If we remember earlier, with 5.7 meters of a fixed structure and at 30 degrees tilt angle, we had, I think, a performance ratio of around 70%. So just by changing the tracker type or the structure type, we already exceeded that by far. And I would assume that for our 75% performance ratio earlier, and I will just compare this now. Yeah, so it's also 85.8%. So for trackers, you can imagine, you can expect a performance ratio much higher than 75% usually, even higher than 80%, I would say. Is there any other question?
Yes. So another question they're asking, in case that there is not a predefined value, like the performance ratio for the working example that you have just shared with us, Julian, which figures can we compare in order to decide for the optimal pitch?
Very good point. So, I mean, from my understanding, I would of course go for the shading. So what I mentioned earlier here, the array shading, right? So we have the array shading here. For trackers, it's usually 0% because they follow the sun, right? So in case of trackers, it might be not the right comparison. And the next one, the next kind of parameter I would choose is, it would be the LCOE. It of course depends how you define your LCOE. So if you compare the LCOEs, you have to have a kind of proper cost model which you trust, and which you kind of also trust that it changes according to your pitch distance. So if you have that ready, maybe you don't have a performance ratio goal, but you maybe have an LCOE, then this is something you can also find in the internet, some other comparison values. So I would go for that one. And then overall, and that's why I mentioned the GCR as well, this is something, it's always a good indicator, I would say. So I just remember that in some countries, it's compulsory to have 60%, but not more. So if you have more than 60% ground coverage ratio, this would mean that the whole environmental and the whole wildlife on that area is kind of prohibited to kind of grow and be maintained. So I would also go for that ground coverage ratio. And just to quickly show you that, if I jump into one design in pvDesign, I can go to layout, and I can see the different options here. I can go to the distances where we changed our pitch distance. And in this case, we have a GCR of 40%. So we could even go higher. And I would say that this is kind of a good indication. If you don't have a performance ratio you want to achieve, I think this is a good point as well. So I would say shadow, array shading in case you don't have trackers, GCR, I would think that works for all the structures, and LCOE if you trust that cost model you have.
Perfect. Thank you. And speaking of which, you mentioned earlier the levelized cost of energy, and we got a question that is asking, how does pvDesign calculate the levelized cost of energy? And does the performance ratio value depend on the DC-AC ratio?
Okay, that's a good point. So the first question, how does it calculate the LCOE? And of course, I mentioned you have to have a cost model you trust. It's here on the top right on the costs. So what do we do in pvDesign? So first of all, we have a CapEx sheet for every country. In this case, we're in Sweden, so it's Sweden here, and we take that from IRENA. It's mentioned here. IRENA is the renewable energy agency. They provide us with CapEx sheets, and what you can see here, basically, you can see some entries. You can see the module and the inverters. You can see the racking and mounting, and all of that. The calculations are based on the main peak power. And of course, this is helpful to kind of also to compare it between different plants, because based on your peak power you installed, you can then have a certain price per unit. So if you don't change anything here in pvDesign, if you don't change the OPEX, if you don't change the currency, because right now we're in US dollars, if you change that to Swedish krona, to euros, any other currency, of course it will change. But if you just leave it like this is how we calculate the LCOE. And of course, what can you see directly? That the LCOE is only dependent on your peak power. So if you install more peak power, then the LCOE goes up. If you do less, then I mean it has a direct relation, right? So we know this is kind of a good first start, maybe. But of course, if you instead would calculate the costs not based on peak power here, you would switch it to the number of modules, number of inverters, because sometimes having a bigger pitch when you have less modules, that can affect it more or less. Or if you have a smaller pitch and you have to install more, or you can install more modules, that might not mean that you have to install more inverters, of course. So that number can stay constant if you base it on the number of inverters. So this is exactly the way you should modify the cost and LCOE analysis. And as a next step, you can, of course, and that's another feature in pvDesign, you can just create your own private one. So you can just take one of those example sheets and just modify it as you like, as you wish, and then have a better cost module. Maybe Ghada, can you repeat the second part of the question? It was related to DC-AC ratio, right?
Yes, it was asking, and sorry, and does the performance ratio value depend on the DC-AC ratio?
Yeah, the performance ratio does not depend on the DC-AC ratio. So DC-AC ratio, I can just jump here. It's a layout tab. You can have an overview in the power requirement section here. This is where you can define the DC-AC ratio. In this case, we defined 1.3 as our goal, and we allowed the software to connect our inverters in a little more flexible way. So basically, DC-AC ratio means how many modules you connect to your inverters, and the performance ratio is more related to how much of the irradiance, so the global irradiation, how much of that is kind of converted into energy. So based on how your tilt is, how is the shadowing overall, so how much energy do you get out of it? And if I'm just thinking, of course, if you have a certain DC-AC ratio, it might be the case that at low sun elevation angles, you have not the optimal voltage for the inverter. So now I have to actually rethink my answer, because I think that could be an effect. If you have low sun elevation, then of course the voltage in your inverters depend on how many modules are connected, of course, how many strings. And if you have a higher DC-AC ratio, then at lower sun elevation angles, so at less irradiation, you can still perform. So I would say, yeah, it has an effect. It has an effect. Sorry, that was the wrong start, but while explaining, I managed to identify how it's
Yeah, and
correct.
you actually answered also another question that asked if the optimal pitch depends on the PV module. So 2-by-1, so great one. Thank you, Julian.
Yeah, no, of course.
We have another interesting question. So we've been asked, does pvDesign work with its own database for the irradiation values, or do you introduce it manually? Which database would you recommend for Nordic countries? he have seen that we have introduced PJS on the slides.
Yeah. Yeah, that's of course the most important question. It's where do we take those values from? Can we trust those values? How does it look? For that, I would just jump to the first tab here. It's called the location tab in pvDesign, and you have then the option to upload your Meteor files. And as already mentioned, we take pvGIS hourly values. So very important to notice here that currently in pvDesign we support monthly and hourly values. Of course, the monthly values would have to be generated into a synthetic file to create those hourly values. So usually we recommend hourly, but currently we also work on sub-hourly models as well. And then if I open our databases here, so if you're a user of pvDesign, you will get pvGIS and NASA as the databases we provide for you. You can already see that the irradiation values, they differ between those databases. And then of course you can add more. You can add the 3 databases here if you want. You can also upload your own local, your private generic ones. So if I scroll a little bit, I can see different, let's say, templates. So Meteor norm, hourly values, generic values, and these are the ones I was referring. So if you have some own generic hourly values from the irradiation, you can upload them here. And then about the question, what I would recommend for the Nordics. So from the feedback we receive, the pvGIS is usually better for the European, for Europe in general. The problem is, I mean, those values right now, they were taken from the year 2005 and to 2020. So this is the range where the whole irradiation values are taken from. I would recommend that, to be honest, but it depends who you trust more, I would say. But usually with pvGIS, you will get a good value for the Nordics. But of course, if you have maybe a bigger range, a larger range from maybe 2000 to 2020, and you generate a synthetic TMY, so typical meteorological year file, that could be even better. So again here, and this is the whole idea of pvDesign in general, you can change that and just create, let's say, create 10, 20 different designs with different Meteor files as your input, and just compare those and then kind of find the optimal one. I think that's a powerful result you can get.
Thank you, Julian.
No, of course.
That's a very insightful way. So we have about 5 minutes left, so we have room for 2 more questions. I would like to ask you, Robert is asking, can he create some amount of designs with different tilt angles to compare them?
Mm-hmm. Yeah, that's a good point, because right now, I mentioned in the beginning of the slides, I mentioned that we have different parameters affecting the shading losses, and of course, if we change the pitch, that's one target, one idea, one strategy, but the tilt was neglected completely. Yeah, this is possible. So if I do the same process of generating multiple designs, you have the pitch, what we did before, but you can also jump to the tilt angle here. In this case, it's disabled, and I mean, that's clear because we have trackers selected. They are moving, so we don't have any fixed tilt here. And we'll jump to an example where we have fixed structures. And when this is zooming in, now we can click here. We can jump straight to the tilt angle, and this is basically exactly what the question was referring to. So what you can do is, we have 30 degrees. We can maybe start at 25 as an example and do a very similar process. We have certain step values. We can change those and then reach 34 degrees tilt. And then we have 2 options. We have the first option. We can keep it at a certain pitch. And what I remembered from our designs we created, our optimal pitch earlier was 6.7 meters to achieve that 75%. And now what we could do is we can just take the 6.7 meters, run the same batch design here, and just going from 25 to 34 degrees tilt. So yeah, that's one idea. The other idea is to not only change the pitch, but also not only change the tilt, but also change the pitch. So in this case, we start with very high values here, but just assuming with the 30 degrees, this is this row here, we had 6.7 meters earlier. So what we can do is we could see, okay, we can say, no, I want to have maybe 6 meters here, maybe I want 6 meters below, and I want 7 meters above. So this could be some idea. I mean, of course, this will, there is no pattern here. You have to select that. So usually I would recommend to first start with the same pitch and just change the tilt, because this is just more clear, I think, to compare. But there is another option as well, as I just showed. And then, yeah, if I generate this, and this is super interesting, actually. I would like to see the results. What happens if what performance ratio do we get?
Isn't this a new feature that we just came out with?
Yeah, good point. Yeah, I mean the batch design that was out for a long time already, and users really liked it, but they were always missing more options. For example, that tilt. So that's why we came up with it 2 days ago, actually. So quite recently.
Yes, it's very nice to see it in action.
Yeah, it's perfectly suits the webinar in this case. That's true.
Yeah. So we have about 2 minutes left.
Yeah.
And maybe we can cover just one last question. I think it's straightforward. Does the program calculate the inner roads required for O&M automatically?
Yeah. Maybe let's cover that first, because that's a good question. If I click on an existing design, what happens? You select all the parameters, you select all the equipment, everything you want, you can select and define in pvDesign. And then if you generate the design, what happens automatically is that road placement and the power station placement. So what we can see here is the red boxes, I would say. They are the power transformers. So this is where we transform from low voltage to medium voltage. And then all those medium voltage lines are connected to one substation here in purple, where we transform to high voltage if wanted or if required. We can also maintain medium voltage if the user wants that. But yeah, regarding the roads, in this layout, it's only a line, but in our AutoCAD files, which we provide, it's not a line, it's a road with a certain width the user defined. And yes, this plays completely automatic. You can change the road layout though. You can change it if you want to have it horizontal, vertical, if you want no roads at all. That's possible for small areas. You can also select if you want to combine it with perimeter roads, but that is it, and the rest will be done automatically for you. Then sometimes users, they ask, okay, why? So how is it deciding where to place the roads and the power stations? And what you can see here, it's usually placing them so that the overall cabling is minimized, so you don't want to waste cable length. So usually you place it quite in the middle to just reduce string cables, low voltage cables. Yeah, but good point. And maybe just follow up with the last question where we wanted to check the results for our tilt changes. I will just mark these designs here quickly. I think that's enough. Compare them really quick. And if I scroll down, I can see that our pitch remained the same. That was our goal. But we can see that the tilt here is basically, in this case, from 28 degrees up to 34. We have our 30 degrees right in the middle. This is what we achieved earlier, 75%. But just by changing our tilt, we could go up to 76% just by changing the tilt 2 degrees. So yeah, of course, this is very powerful to not only combine and check the different pitch distances, but combine it with an analysis of the tilt as well. Perfect.
Perfect. So
thank you for the questions. Really helpful.
Yeah, we finished with our timing, so we don't want to make it any longer. Thank you so much, Julian, for your time and for your presentation. It was really insightful, and I hope all of our attendees had a very insightful presentation as well. Just as a reminder, we'll be sharing with you the technical documentations of the specific case scenario that we have showed you earlier, the one that Julian showed you, so you can check out the documentations that are being generated after you finish your design. And yeah, for any details or demonstrations, please feel free to contact us. We'll be very happy to run into a conversation with you. Thank you so much for your time. Thank you, Julian.
Perfect. Bye-bye. Thank you so much.
Bye. Have a very good day.